Good morning, everyone. So this week we are going to be focusing on acids and bases in lab, which was a major topic in Chapter 5 of our lecture. And so we're going to be differentiating between acidic, basic, and neutral solutions by testing the pH measurements for several solutions. And we're going to use 3 different methods to determine the pH of various solutions. In addition to determining the pH of various solutions, we're also going to observe several chemical reactions involving acids. And so these chemical reactions that we're going to be monitoring, they're going to involve acids reacting with several different substances. And so you are to download both the introduction and procedure document as well as the lab report form before class. And you are to read the introduction and procedure material and then also complete the pre-lab questions that are on your lab report form. So today there are several videos and pictures that you'll view in order to complete your lab report form. And then at the end of the lab, when you're done completing your lab report form, there'll also be 6 questions that you would need to answer also on that lab report form after you've collected all of your observation data for the chemical reactions. And so once your lab report form is completely finished, then you can go here and click on Acid-Base Lab and upload your single PDF file or your single Word document to the Dropbox. So let's take a look at the introduction and procedure information, as well as a quick look at the pre-lab questions. So the purpose of this lab is for us to use the pH scale to measure the acidity or basicity of a substance. And we're going to measure the pH 3 different ways. And then we're also going to study some chemical reactions involving acids reacting with a variety of different solutions. So shown here is a list of materials and chemicals that you will observe being used in the videos and pictures. So in the lecture, we learned about acids and bases. And we learned that we can characterize acidity and basicity based on determining the pH value for a solution. The pH value is a measure of the concentration of hydronium ions in solution. Hydronium ion has the formula H3O+. We also learned in the lecture that the hydronium ion is equivalent to a hydrogen ion, H+. And we also learned that the hydrogen ion can also be defined simply as a proton. So when the proton H+ gets solvated or surrounded or dissolved by water molecules, that is what produces the hydronium ion. And so when we want to analyze the concentration of a solution, we learned that the more popular unit used in chemistry for concentration is molarity. So when we are expressing the concentration of a substance, we put it in brackets. So those brackets mean concentration of. So if we put H3O plus within the brackets, that means the concentration of the hydronium ion. And so therefore, the concentration and the pH are inversely proportional to each other. So what that means, the higher the concentration of hydronium ions in a solution, the lower the pH, and therefore the more acidic the solution. And so the way in which we relate the concentration of H3O plus, which is equivalent to the concentration of H plus, is that it's equal to 1 times 10 raised to the negative value of the pH. So raised to the power of the negative pH. And of course, concentration will be in units of moles per liter, which is molarity. So therefore, we can rearrange the equation and get an expression for pH. It will be the inverse of the base 10 function, which is the log function. So the pH is equal to the negative logarithmic value for the concentration of H plus. And of course, you can also just put the concentration of H plus, because the H plus and H3O plus concentrations are identical. So therefore, when doing this calculation, to access the base 10 function on your calculator, you usually have to hit the shift button on most calculators and then hit the log button, LOG. And then for the other equation, you'll just hit the log button on your calculator. And then you'll put in the value for the concentration of H3O plus. You'll get a negative value. And then you take the negative of the negative, and that will give you a positive value for the pH. So pH is always going to be a positive value, because we learned that our pH scale usually ranges from 0 to 14. Now we're going to use indicator as one method to determine pH. Then we're also going to use pH paper as the second method. When you buy pH paper, it's going to give you a key or a colored scale, which tells you what color is associated with each pH value. And so when you add some solution to the pH paper is going to be therefore converted to a specific color. And that color is going to match the pH value. And so, ranging from 0 to 14, if a solution has a pH between 0 and 7, then it is acidic. And to get more specific, a pH value between 0 and 2 is very acidic. Between 2 and 5 is moderately acidic. And then between 5 and 7 is slightly acidic. Value equal to 7 is neutral. And then if the pH is greater than 7, so between 7 and 14, then it is basic. And then more specifically, between 7 and 9 is slightly basic. Between 9 and 11 is moderately basic. And then if the pH is greater than 11, it's very basic. And so this table lists some common substances and their pH values. And so we notice that a lot of things that we drink and that we eat, you like lemon in your sweet tea, a lot of these substances that we eat and drink, they are acidic. Purified water, which will be bottled water or water that has been filtered to remove dissolved ions, only pure water will be neutral at a pH 7. Tap water is actually slightly acidic. Tap water has a pH of between 5.5 and 6.5, depending on where you are. But normally tap water will have a pH close to that of rainwater and milk, somewhere between the pH values of rainwater and milk. Seawater and ocean water, they're very salty. And so those ions dissolved in the ocean and seawater, those ions make seawater slightly basic with a pH of 8.5. And so we talked about the fact that we're going to use 3 different methods to determine pH values of several solutions. The first method is to use a chemical indicator, which is just a dye that has a specific color. And so the purpose of the indicator dye is to turn the solution that you're testing a specific color. And whatever color that solution is turned into due to the addition of the indicator, that's going to tell you a pH range. So using the indicator will not be able to tell you the exact pH number like we see here, but it will be able to tell you a pH range. In other words, it'll tell you whether or not the pH of the solution that you're testing, if it's between 4 and 6, or if the pH is between 8 and 10, or if it's between 2 and 4. So the best you're going to get as far as determining the pH using an indicator is a pH range. However, using the second method, pH paper, you'll be able to determine the exact pH value, but only certain to a whole number value, not certain to a decimal place value like we see here in this table. In order to determine the pH value, I apologize. I got disconnected somehow. I'm not sure how that happened, but I am back. I'm hoping you can hear me.
We can hear you.
Great, thank you. So I'm not sure exactly the point I was cut off, but I was explaining that when you use an indicator to determine the pH of a solution, you can only determine a pH range and not an exact pH value. However, when using pH paper, you can determine the pH exactly, but only to the nearest whole number. You won't be able to determine the pH to any number of decimal places using pH paper. So for instance, if you add a few drops of your solution onto a piece of pH paper, and you'll be able to differentiate whether or not the pH is 2, whether it's 3, whether it's 4, so on and so forth. But you won't be able to determine whether it's 2.2 or 3.6. You won't be able to determine it that accurately, but only just to the nearest whole number. And that's based on the color key that comes with the pH paper. However, if you want to determine the pH more accurately, you're going to have to use a pH meter, which is also called a pH probe. And so with our pH probe, you will be able to determine the pH to 2 decimal places. And I am sharing my screen. Are you able to see my screen?
No, I just see a black screen with your initials on it.
Okay, I'm going to stop sharing.
I can see your screen.
Now, can you see my screen?
I can see it.
Great. And so we talked about acids being able to react with a great variety of substances. And so acids are found naturally in our digestive system, in our stomachs. And that acid that's naturally there helps to digest and break down our foods to release the nutrients that are in the foods that we eat. So that's acid being very, very helpful when it comes to our digestion. However, reactions that acids have with substances can have some adverse effects. For example, when there's acid in the rain, which we call acid rain, that acid rain can lower the pH values in small bodies of water like rivers and streams where fish and other aquatic life live, and therefore it could be detrimental to that aquatic life. And also acid rain can damage statues and monuments that are made of a variety of metals like zinc, copper, aluminum, and iron. And we're also going to see acid reacting with egg white, which is composed mainly of protein. And so if we were on campus and doing the lab on site, we would need to follow some very important safety precautions because we would be working hands-on with acids and bases. So we would want to wear gloves. We would definitely want to have our goggles on from start to finish. And then also make sure that we're properly attired, making sure that we have shoes that completely cover our feet and that we have pants on or shorts or a skirt on that at least reach our knees so that if we did have a spill in our labs, that acid would not go directly onto our skin, but we would have that protective clothing layer to protect us. And so we're going to use 3 acids in our chemical reactions of acids with substances. We're going to be using hydrochloric acid, HCl, and then we're going to be using sulfuric acid, H2SO4, with 2 different samples of that H2SO4 that are at 2 different concentrations. And so those were some of the safety precautions that we would be very mindful of if we were actually in the lab. And so now to quickly go over the first part of the procedure before I send you to your group meeting rooms to watch the videos and view the pictures. The first part of the experiment is determining the pH using the 3 different methods. The first method you're going to use is using 2 different indicators. And so once you watch the videos and you observe and write down what color the solutions change to when indicator is added to them, you're going to use this scale as a guide to determine the pH range of each solution based on the color that it changes. So as stated, we're going to be testing 2 different indicators, and we're going to place 2 or 3 drops of each of these types of indicators in solutions of tap water, ammonia, and club soda. So when we put methyl red in each of those solutions, if it stays red, then that means the pH is going to be on the low end of the scale. So if adding the methyl red to the solution turns the solution red, that means you're in this range. If adding the methyl red causes the solution to turn orange, then you're going to be in probably the 6 to 8 range. However, if it turns yellow, then you're in about the 4 to 6 range. So that's your methyl red indicator. So you're going to watch a video and you're going to see me add methyl red to tap water, ammonia, and club soda. If the tap water, ammonia, club soda, if they turn red, that means the pH is between 0 and 4. If those substances turn orange, that means the pH is between 6 and 7. If those solutions turn yellow, that means you're in the 4 to 6 pH range. The next indicator is phenolphthalein. So when you add the phenolphthalein to the tap water, ammonia, club soda, if you get a light pink color, that means you're in the pH range of 8 to 10. But if you get a hot pink or a bright pink color, that means you're between 10 and 14. Now, when you add phenolphthalein, and if you don't get any color at all, if it's colorless, then you're in the acidic range. So if adding the phenolphthalein doesn't do anything to the solution, if it started out colorless and then you add phenolphthalein, and if it remains colorless, that means you're dealing with an acidic solution. And the only thing you can say is somewhere between 0 and 7. It's acidic. That's the only thing you can determine. If adding phenolphthalein does absolutely nothing. If the solution started out colorless, you added phenolphthalein, it stayed colorless, then all you can say is that my solution is acidic. It's somewhere between 0 and 7. You can't get any more specific than that. But if the phenolphthalein turns the solution pink, that means it's slightly basic, between 8 and 10. Or if it turns at a hot pink or a bright pink, it's strongly basic, between 10 and 14. So that's how you will go about completing the determination of pH using indicator. Then next, you'll be determining the pH using pH paper. Again, you'll see a video and you'll see what color the pH paper changes. You'll see a copy of the color guide that comes with the pH paper. And based on what color the pH paper to change to, you'll use that key, that guide, to determine the pH of the solution. And then finally, using a pH meter or a pH probe to determine pH, you'll view the pictures and you'll read the pH values that are shown on the computer screen from those pictures. And so at this time, I'm going to take a look at the lab report form. Your lab report form, you need to have the pre-lab questions. They should have already been done at the beginning, before the beginning of the lab. So make sure that you're turning in this complete lab report form with the pre-lab questions completed. And then here is where your actual report starts. Make sure you put your name as well as the group members that you work with today on your report form. And then here you'll be completing tables A, B, and C for the first part of the lab, filling in the color that the methyl red indicator caused tap water, ammonia, and club soda to change to, and then do the same for the phenolphthalein indicator. And then based on those color changes, give the pH range for each of those 3 solutions. And then using your pH paper based on the color change that occurs and using the key or the guide that comes with the pH paper, give the pH value to the nearest whole number. However, if you have a substance and it seems like the color that the pH paper changed to appears that it fell between two values, you can give a range. You may find that a couple of these substances may fall between two pH values based on the color that the pH paper changes to. And if that's the case, you can give a pH range. And then finally, the pH meter, table C, just simply write down the values for the pH to 2 decimal places that you see on the computer screen in the pictures. And so before I send you to your group meeting rooms to do the first part of the lab, are there any questions about the pre-lab questions number 1 through 9? In reading the introduction and procedure information, you should have been able to answer these questions just fine, as well as the things that you've learned about acids and bases in your lecture. Any questions about the pre-lab questions? Okay, so if there aren't any questions about those, you can go ahead and go into your group meeting rooms. And so when you go into your group meeting rooms, make sure you got your eLearn lab page open. And if you go to week number 12, you'll see where there are the videos and pictures for the acid-base lab. You'll want to click on that little arrow, and that'll bring up all the videos and the pictures. So you want to first watch the video for determining pH using indicators, then the pH paper, then the pH probe. And so you'll want to go through those first 3 sets of videos and pictures. Fill out your tables A, B, and C on your lab report form. Once you're done doing that, return to the general room. We'll have a quick discussion, and then I'll introduce the last part of the lab. Okay, most of us are back in the general room. Are there any questions about data tables A, B, or C? The pH determinations using indicator, pH paper, and the pH meter. Again, any questions about determining your pH range for part A using an indicator? For part B, using your pH paper, as I stated earlier, if it appeared that the color that the pH paper changed using the little guide, if it appeared that it could have been between two different colors, then it's okay to use a range. For example, the lemon juice. I would have said that it's maybe between 2 and 3. They have that dark red color change. Or another example, like the Sprite. For me, it looked like it could have been between 3 and 4. And the vinegar, same as the lemon juice, between 2 and 3. So it's perfectly okay to have a range for the pH paper determinations, or a whole number value, like the ammonia. For me, it seemed like it was right on 11. So for part B, it's okay to have just a whole number, or if you felt like it fell between two of the different colors, you can list a range. And so, of course, the pH meter part was straightforward. You just simply read the readings that were shown on the computer screen. The pH probe or pH meter that I used, if you could see in the pictures, I had it connected to this device, this little white box called a Vernier Lab Pro interface device. And then I had another cord connected to a specific channel in that little Vernier interface device that I plugged into the USB port of my computer. And then there's the software program on all the computers in the lab called Logger Pro. And with Logger Pro, you can use many different types of instruments and probes and connect your computer to those and your Vernier interface to those probes, or like a pH probe or a temperature probe, a spectrophotometer, so on and so forth. And then you can use the software on the computer and you can monitor the temperature changes that take place during a reaction, or measure pH values like we did in this lab, or determine the amount of light that gets absorbed by a colored solution using a spectrophotometer connected to the Vernier Lab Pro interface device. So that little device not only will allow you to determine pH values to great accuracy, up to 2 decimal places, but you can also determine other parameters like using temperature probes and determine the amount of light absorbed using a spectrophotometer, and many, many other things. A conduction meter to detect how good of an electrical conductor a solution is by the measuring the voltage or the electrical potential that's created by that solution. So you can use the Vernier interface device along with the Logger Pro software that we have on our lab computers to monitor many different physical and chemical properties of a solution or of a chemical or other substance. So the last part of the lab is observing reactions between acids and common substances. The common substances that you're going to be observing reacting with acids are marble chips, and then metals like zinc, copper, iron, and aluminum. And then you're also going to monitor acids reacting with protein that's found in egg whites. The source of iron, we're just using common staples that you use in your stapler. Those are made of iron. Then we have copper metal, some zinc metal pellets, and then some little marble chips. Now, there are only 3 of these 4 acids that we're going to be observing reactions for. We didn't have any of the nitric acid set up for us, and so we are eliminating the nitric acid. So in the tables for nitric acid, you can just put Na for not applicable. So the 3 acids that we are going to be observing reacting with these common substances are 6 molar HCl, as well as 6 molar sulfuric acid. That's going to be your concentrated sulfuric acid. And then we're also going to be using a solution of sulfuric acid that has a smaller molarity than 6 molar, and specifically 10-fold smaller. Its concentration is only 0.6 molarity. So we call this a dilute solution of sulfuric acid at only 0.6 molarity, whereas the concentrated sulfuric acid has a concentration that's 10 times higher at 6 molarity. And so you're going to be making initial observations of the reactions between these acids and each of the substances. And then I let the reaction sit for way over an hour. And then I took another video of each reaction at a later time. And so then you're going to write your observations for each of these reactions after those reactions have taken place for more than an hour. And so in making your observations here in these data tables, you don't have to write a whole lot. You can write a few words, no more than a sentence is necessary. So just basically tell me what you see. So tell me what you see happening when 6 molar HCl is added to the marble. Do you see fizzing? Do you see bubbling? Do you see a color change? If the marble started off as, of course, a white solid substance, what is happening to it? Are the marble chips getting smaller? Things like that. That's what you're going to write in the data table for your observations based on what you see happening to each substance. Is the size of the substance changing? Is the color of that substance changing as a result of the acid reacting with it? And then you repeat those observations for each of the other substances. For the zinc, the copper, the staples made of iron, and then aluminum, and the egg whites. So if you go to our eLearn Lab site, where the videos and pictures, where you access for the pH determinations, underneath is a set of videos for reactions of these acids with our common substances. And so the first videos are for the initial observations, of all of the substances except for the egg white. And then the next video is the reactions of the common substances minus the egg white with the acids after those reactions have sat for more than an hour. And the last two videos just involve the egg white. Your initial observations of the egg white reacting with the 3 different acids, and then of course your final observations. When I first videoed the lab, I had forgotten to bring egg white from home. So I had to wait until the next day to do the egg white reactions. So go ahead and go to your individual group meeting rooms, view the videos for each reactions for each acid with those common substances, and then fill out your data table with your observations. Again, you don't have to write a whole lot. Basically, just tell me what you see. What changes are happening to each of the substances? Do you see fizzing? Do you see bubbling? Do you notice a color change? Is the substance getting smaller, especially like the zinc or the acid chips, the pieces of metal? Do the pieces of metal get smaller? Do they change in some way as a result of reacting with the acid? And so this part, I would expect you to be done with this part by around 11. So let's come back to the general meeting room by 11, and we will answer any questions that you have about your initial and final observations made for each of these reactions. And then we'll discuss the post-lab questions, numbers 1 through 6, that you need to complete before you upload your completed report to the Dropbox. So go ahead and go to your group meeting rooms. I'll be coming by each of your meeting rooms to ask you if you have any questions. And then let's meet back in the general meeting room by around 11 a.m. If everyone's done before then, I'll be monitoring the general meeting room. And if everyone is back before 11, then we will start discussing this part of the lab once everyone gets back to the general meeting room and talk about the last 6 questions. I think most of us are back in the general meeting room at this time. So, do you have any questions about any of your observations that you made for the reactions of those 3 acids with the common substances? Any questions about observations? If there aren't any questions about observations, the last thing you need to do to complete your lab report is to answer questions 1 through 6. Question 1 is based on that equation that was provided for you in the introduction and procedure material. So for question 1, you're asked to calculate the concentration range for moderate acids. Also in the introduction and procedure information, you are told that a pH between 2 and 5 is moderately acidic. So what you need to do for question 1 is calculate the H3O plus concentration at a pH value of 2 and the H3O plus concentration for a pH of 5. So that's what question 1 is asking. So at a pH of 2, this is how my equations would be set up. It's going to be the base 10 function raised to the negative 2 power. And then for a pH of 5, the concentration of H3O plus, which is the same as the concentration of H plus, is equal to 10 to the negative 5th power. So those will be the values for concentration of H plus or H3O plus at those pH values. The lower end is 2 for moderate acids. The upper end is 5. So therefore, the concentration of H3O plus ranges from 0.01 molarity for a pH of 2 to 1 times 10 to the negative 5th molarity for a pH of 5. So it's clear that the more concentrated or the higher the molarity of H3O plus, or the higher the concentration of H3O plus, the smaller the pH, which means the more acidic the solution is. So remember we said that the base 10 function or logarithmic nature of the equation means that pH and concentration of H plus or concentration of H3O plus, they are inversely proportional. So the higher the concentration of H3O plus in a solution, the smaller the pH, which means the more acidic the solution is. For question 2, your observations for your reactions. How did the 6 molar H2SO4 reactions compare to the 0.6 molar H2SO4 reactions? The 6 molar, of course, is the higher concentration. The 0.6 molar is the lower concentration. It is more dilute The 6 molar is more concentrated. So how did the concentration affect the reactions? Did you notice that one of the reactions was faster than the other? The 6 molar reactions versus the 0.6 molar reactions. And for what substances did you view that? You know, the marble chips, after you did your later or your final observations, were there still some marble chips visible in the 6 molar H2SO4 reaction, or were they all disappeared? Have they all been broken down by the acid? So that's how you determine the rate of the reaction. How fast did the marble chips react with the 6 molar H2SO4 versus the 0.6 molar? Did you observe some of the marble chips still remaining? What about the zinc? What about the iron? And then one thing you should have noticed about the copper, I don't think any of the acids reacted with the copper. So that copper metal is pretty unreactive with acids, which is why copper metal is expensive. It's used for special purposes in wiring and things of that nature, because it's non-corrosive. It doesn't react with acids. Acids don't break it down. Question 3, marble is a component of lots of building materials, kitchen countertops and tile and things of that nature, but also statues and monuments are largely made of marble, especially in Washington, D.C. So if you've got acid in the rain, and then when it rains, it's going to react with the marble in the statues. And so marble is calcium carbonate, CaCO3. Acid rain is composed of sulfuric acid and nitric acid. Well, we didn't view the nitric acid reactions, but we did view H2SO4 reactions. So the H2SO4 is going to react with the calcium carbonate, and calcium carbonate is a weak base. And so when the reaction takes place, 2 of your products are going to be water, H2O, and an ionic compound, which we also call a salt, calcium sulfate. But you also get some carbon dioxide gas. That is a product as well. So that's what happens to statues and monuments over a long period of time if they're constantly being subjected to acid rain. If there's acid in the rain every time it rains, then over several years, those statues are going to start to change in their appearance. They're going to start to break down. They're going to start to fade, and the color, you're going to see a color change. You're going to see the lettering and engravement on the statues and monuments. Those are going to start changing. And that's going to be evidence that the marble, the calcium carbonate that those statues are made of, they are getting broken down by something. And that something is the acid that's in the rain. And so again, what effect do you expect concentration to have on the action of the acid rain in the marble? So if acid rain is a bigger problem on the East Coast versus the Midwest, then would you expect the statues and monuments in Washington to be in greater danger than a statue or a monument in Chicago, for example? And the reason why acid rain is a bigger problem on the East Coast is because the prevailing winds, they blow from west to east. So acid rain falls at a more concentrated nature on the East Coast versus the West or the Midwest because of the direction of prevailing winds carrying that moisture to the East Coast more so than the West or the Midwest. So therefore, that's why the East Coast has a bigger problem with acid rain than the West and East Coast, the West and the Midwest. And therefore, the more concentrated the acids in the acid rain, then you would expect the rate of the acid rain reacting with statues and monuments should also increase. Now, in your observations, we had zinc metal, copper metal, iron, and aluminum. Did you notice aluminum reacting differently than the other metals? And if so, in what way? Did it react faster than the other metals? Did it react slower? And then finally, aluminum easily forms an unreactive oxide coating that acts as a layer of protection, protecting the aluminum from the acid. So does this account for what you observed as far as differences in the way the acids reacted with the aluminum versus the zinc and the iron, for example? So those are your 6 questions. I tried to give you a little overview and give you insight on what the question is asking and what response you're expected to give to each of the questions. Are there any further questions or concerns about numbers 1 through 6?
Can you kind of repeat what you said for number 2 about the concentration affecting the rate of reactions?
So you tell me what you think based on what you saw. You had 6 molar HCl, which is a higher concentration, and you also had 0.6 molar sulfuric acid, which of course is a smaller concentration. Take a look at your marble chip reactions with each of those acids. That's a good one to look at to compare concentrations. Do you think the 6 molar H2SO4 reacted faster with the marble chips than the 0.6 molar? And if so, what evidence do you have from your observations that that's true? You may need to go back and look at the video to answer that question.
Okay, looking back at the chart helps explain it more.
Okay, does that answer your question now?
Yes.
Okay, so if you had some marble chips still left over, that means you had a slow reaction. If the later observation, those marble chips were gone, that's a fast rate of reaction. Did that answer your question?
Yes, ma'am.
All right. Are there any other questions on numbers 1 through 6? If there aren't any other questions, if you want to go back to your group meeting rooms to finish up your report, you can do that. If you feel comfortable that you've gotten everything that you need and you want to go ahead and leave the meeting room, feel free to do that as well. Your lab report needs to be completed, including the 6 questions at the end, and then upload your single file to the Dropbox by 11:59 p.m. tonight. If you have further questions, feel free to ask them now. You're welcome, Laura. So if you don't have any further questions, you're free to leave the meeting room. Have a great weekend. Make sure you upload your report to the Dropbox before midnight tonight. And I'll see you either in class next week or in lab next week. If there aren't any other questions, I'm going to go ahead and stop the recording.